so today we are working with Newton's laws. Isaac Newton discovered 3 laws of motion that are still used today, and actually the foundation for a lot of our principles in physics. And so we will look at each law individually, and I'll show you several demos to go with each law. Okay, so Newton's first law is an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by another force. This idea is called inertia, and that's the resistance to change, so Newton's first law is often called the law of inertia. Okay, so I have some common examples for you that you probably all experienced, or at least are familiar with. So first one would be if you're riding in the car and your parents hit the brakes really hard and you jerk forward in your seatbelt. That is inertia. Your body was in motion and it wanted to stay in motion, and so the car came to a sudden stop and your body continued forward until the seatbelt stopped it. Same thing goes on why you don't fall out of a roller coaster, is that spinning motion is actually keeping you in your seat. Why astronauts and fighter pilots experience what we call G-force, which is what we talked about last week when we were doing the helmet study. So G-forces are pushing them back in their seat as they're taking off because they're rapidly changing. And then we also have when you feel squished riding in the scrambler at the amusement park. Your body was going in one direction and suddenly the ride changed directions on you and swung to the side and you get squished up to the side. So the greater an object's mass, the more inertia it has, the more it is resistant to change. Either it wants to stay still or it wants to keep moving in the direction that it was moving. Okay, this is one you're all familiar with, and a lot of you have used it in my class already. This is called Newton's cradle because it demonstrates Newton's first law. So the balls right now are at rest. I'm going to take the first one, and if we think about what we did on our first lesson, we added potential energy by adding height. The other ones are still at rest, and now I'm going to drop it down. So it's transferring that energy back and forth. The ones in the center want to stay at rest. Okay, so for this one, we have a stack of quarters here, and they're at rest. They don't want to do anything. I'm going to take this 1 quarter, I'm going to flick it at the stack, and it should drive out the bottom one, and the rest of the stack should stay still and just drop down because they're staying at rest. So we can do it again. Whoop, I missed. There we go. Like that one, it dropped right on top of the one that I shot. Okay, so for the next one, I have glass. It's got a little paper towel on the bottom for padding. Then we have a tinfoil plate. We got toilet paper tube and an egg. Now, if I do it right, I can hit the pan out from underneath the egg and the egg will drop right down in the glass. If I do it wrong, we're going to have egg everywhere. Ready? 1, 2, 3. Okay, so I've got 2 IBC bottles stacked up with a dollar bill in between, and if I pull the dollar bill out fast enough, the law of inertia says that they will stay stacked. Alright, so for our last demonstration of the law of inertia, I'm going to do the classic magician's trick of pulling the tablecloth out from underneath a fully set table. So hopefully this goes well, otherwise I'm going to have some serious cleanup. Okay. 1, 2. Okay, so for our next demo, what we're going to do is take some water and fill up this cup. And then I'm going to spin this board over my head. It's called an inertia board, without spilling the water. So the water's staying in the cup even though we're upside down. If I slow it down, all the water's still in the cup. Okay, Newton's second law says that force equals mass times acceleration. In other words, an object's acceleration depends on its mass and the force acting on it. So in a formula, that would be F equals ma, or A equals F divided by m. So F would be force, m would be mass, A would be acceleration. Okay, so if F equals ma, A is measured in meters per second squared. Gravity is our most common acceleration that we deal with. So gravity is 9.8 meters per second squared, just like we used in our energy equations. M is mass, that's measured in kilograms. F is the force, measured in newtons, or N. 1 newton is the force needed to move 1 kilogram at 1 meter per second squared. Okay, so for our first demonstration of Newton's second law, which is our force equals mass times acceleration, we have a full can of Diet Coke, and then we have an empty can over here. So should be the full can should go much faster and reach the bottom of the ramp before the empty can. Hannah's going to help me out. 3, 2, 1. Okay, so for our next demonstration, I have one small marble, then I have one big blue shooter, and they're going to run down the ramp. So first I got the shooter at the bottom. I've got a little mass. They're going to accelerate at the same speed because they're going down the same slope. A little mass hitting into a big mass, and we're going to look at the speed of the marbles as they run down the track. So 3, 2, 1. Okay, now we're switched them. Got the little marble at the bottom, the big marble at the top, same acceleration because we're going down the same ramp. We're going to look at the speed again. Okay, so in the last one we saw the larger marble hitting the smaller marble was much more effective than the little hitting the big. And so now we're actually going to look at some numbers. So I have a 200 gram mass hanging from the spring sail, and what I'm going to do is I'm going to jerk it up, so we're accelerating the mass, and we're going to see how that changes the force. So mass doesn't change, acceleration right now is at rest, and I'm going to move my hand up and see how that affects the force on the spring scale. Okay, so when I pulled my hand up and accelerated the mass, it showed about 450 grams for that 200 gram weight. Okay, Newton's third law says if one object exerts a force on another, then the second object exerts a force of equal strength in the opposite direction. In other words, for every action, there's an equal and opposite reaction. Okay, so let's look at some common examples that you will be familiar with. One would be the bathroom scale in your house. When you step on it, you're actually pushing a force down, and actually the ground pushes back up against it. Another one would be jumping. In order to jump forward, you actually have to push back with your feet. If you ride a skateboard, in order to go forward on your skateboard, you actually push backward with your leg. And if you play baseball, in order to swing forward, you actually are pushing back slightly with your feet. Okay, One more example from when the research I used to do and the research that my wife still does is in biomechanics. We studied the way that people ran or walked, and we have them step on a force plate, which is like a really fancy, super sensitive bathroom scale set into the floor. With the force plate, it actually tells us the ground reaction force, which is actually the force that the ground is pushing back against us. It's hard to measure the forces going in the person's leg, but we can measure the ground reaction forces for them stepping on the force plate. So this is equal and opposite reaction. For our demo for equal and opposite reaction, I've got a balloon that I filled up with air. For the balloon to go forward, it's got to push the air backward. So, next demonstration is just going to be simple jumping. In order to go this way, I actually have to push back my feet. If I just jump pushing straight up with no backward force, and we just go straight up. So we'll see how far I go forward. Alright. Good for the next one. Now I've taken the ground out of the equation. I'm going to push off from the skateboard. So if you don't believe me that you have to push backward to go forward, this will show what will happen. So I'm still trying to jump this way. Okay, so as you saw, tried to go that way. My feet actually landed on the yellow line. The only reason I went forward is because I was falling forward to prevent myself from landing on my face. But there was no forward motion from the jump. Okay, you're probably all familiar with the story of Newton sitting underneath the apple tree and an apple falls on his head, and that's how he discovered the theory of gravity, or so the story goes. The lesser known story is that in 1665, when he attended university at Cambridge, the university had to close for 2 years due to the plague, kind of like our situation now. So while he was at home, he actually discovered the foundations of calculus, and that white light is actually composed of all the other colors, and developed the idea that later became known as universal gravitation by studying the orbit of the moon around the Earth. So today we just studied his 3 laws of motion, but he was a brilliant man responsible for a lot of scientific discoveries in our world.